Welcome to the European Space Agency, ESA. This is the Robotic Learning Centre, and we're here today to answer some questions about matter. Ever wondered what the world is made of? Or why gold is a different colour to silver? Why oil and water don't mix? Or why fizzy tablets, well, fizz? All of this has to do with matter, how it is formed, and how it behaves in different environments. Matter is all around us, on Earth, in space, and at the farthest reaches of our universe. One important area that we've applied our understanding of matter to is the exploration of space, where astronauts live and work in a weightless environment. We will see that matter can behave differently here than it does on Earth. I've asked friends from Norway, Portugal, Italy, and Greece to lend a hand. And we'll be going on board the International Space Station, the ISS, to get help from Italian ESA astronaut Roberto Vittori and Russian cosmonaut Sergei Krikalev. We'll meet ESA astronauts Andrei Kuipers, Pedro Duque and Frank Divina, and we'll see experiments performed on an ESA parabolic flight, a weightless environment that's a bit closer to home. Hey guys, that looks interesting. Trying out some acrobatics, eh? What's this about, Roberto? Plus and minus signs. Not maths, I hope. The plus and minus come together, but the two plus signs don't seem to like each other. These demonstrations are all about the structure of matter. So, what is matter? Well, anything which has mass and takes up space is matter. As we'll learn later, matter has 3 different states and many properties. The amazing thing about matter is that it makes up everything. The sun in the sky, the water in your pool, everything, distant or near, tiny or huge, is made up of the same basic building blocks. So we are made up of the same matter as stars. Now, of course, it's plain to see that this student isn't the same as her bicycle. This is because the matter that forms the student and the bicycle is organised in a different way. So what is everything made of? They are much too small to see, but crammed into this one glass there are 100,000 trillion tiny particles called atoms. There are over 100 different kinds of atom, each one unique to a particular element. Aluminium, iron, carbon and silver are all elements that you're probably familiar with. Each letter stands for a different element. O here stands for oxygen, H for hydrogen. But what is an atom? Atoms themselves are made up of even smaller building blocks. These are called subatomic particles. If these models were 2 different atoms, then the main difference between them is the number of blocks that we use. There are 3 main types of subatomic particle: the neutron, the proton, and the electron. These particles have electric charges. The proton is positive, the electron is negative, and the neutron, well, has no charge. Electrical charges behave in a certain way. Here, Vittori is a negative charge, and Sergei is a positive charge. What happens? And now we have 2 positive charges. The reaction looks different. This is a fundamental law of nature. Charges of the same kind repel each other, while opposite charges attract each other. In each atom, the heavy protons and neutrons are packed together in the centre of the atom, which is called the nucleus and is positively charged. The lighter, negatively charged electrons are attracted by the protons. However, they are not pulled toward the nucleus as they're travelling fast enough to orbit it, just like the ISS orbits the Earth. The students here are representing the hydrogen atom, in which the nucleus is formed by just 1 proton. Be warned, this demonstration is not to scale. The distances between real subatomic particles are colossal. Imagine that this proton is a cherry stone at the centre of a football stadium, and that the electron is a piece of dust swooping around the stands, and you'll get a good idea of the relative distances within the atomic structure. The electrons have a lot more freedom to move around, and because of this, they influence the way that atoms combine to form different materials. What makes an atom of carbon different from an atom of helium is the number of protons each contains. Atoms are neutral because, usually, there are as many electrons as protons. Let's look at this helium atom. There are 2 electrons circling the nucleus. In the nucleus, there are 2 protons and 2 neutrons. The number of protons and electrons is equal, so that the overall charge of the element is neutral. But if an electron goes missing, we are left with a positive helium ion. And if we get an extra electron, we are left with a negative helium ion. Charge plays an important part not only in atomic structure, but also in how matter reacts and combines. And a lot of what you learn about in chemistry and physics is based on electrical charge. When atoms bond, we call the result a molecule. The arrangement of atoms to form a molecule is called the molecular structure. For example, 2 atoms of hydrogen make up a molecule of hydrogen gas. In this case, they socially share their 1 electron each. When atoms of different elements combine, they form a compound. Here, 1 element is usually the boss and steals, or partly steals, the electrons from the other element. Compounds include water, hydrogen and oxygen, salt, sodium and chlorine, and carbon dioxide. Yes, you've guessed it, carbon and oxygen. Each ball is an atom, and the stick represents the attraction between them. As you can see, each molecule has a different shape. The hydrogen gas molecule looks very different to the water molecule. The shape of molecules affects how they combine and react with each other. Atoms can also combine in big ordered structures called crystals. You can see for yourself how these tiny atoms are arranged in a compound by making crystals. All you need to do is boil sugar and water together and let it cool. Crystalline structures follow the same laws in space, but with a difference. Easy there, Roberto. He is shaking the cube container so that friction will charge the spheres inside. The white spheres become negatively charged, and the transparent spheres become positively charged. The spheres organize themselves in space according to these electrical forces. We can see how structures self-assemble because of this attraction and repulsion. They form anything from simple clusters to complex alignments building up to a crystal-like formation. In weightlessness, these structures do not grow in any particular direction. They create bonds in all directions. On Earth, due to gravity, the structures form in a different way. The charged spheres arrange themselves in a horizontal, 2-dimensional layer because gravity is pulling them down. Different types of crystals can be grown on Earth using simple household items: salt, sugar, and ice. The pretty blue one is made from copper sulfate. Guess you might need a lab for that. Very impressive. See how different their shapes are? This is because different elements were used, and each element has a different crystalline structure. Hey, don't eat too many sweets. Wait until after lunch. Here you can see the chocolates are packed inside the box to take up the least amount of space. This close packing is what happens to atoms in solids. Of course, atoms and molecules are not always close packed. There can be a lot of empty space within a molecular structure. The coffee here is dissolving into the empty space between the water molecules. This is because the water molecules are not as tightly packed as molecules would be in a solid. The coffee diffuses from an area of high concentration to an area of lower concentration. From stones to stars, from salt to snow, from electrons to atoms and molecules, matter can form in different ways to create an almost infinite number of materials with different properties. The variety is indeed amazing. But let's look now at how matter behaves in different environments and under very different conditions. In general, it isn't a good idea to have fluids floating around on board the ISS. This might be fine for small amounts of water, but hot coffee could have painful consequences. Design engineers have come up with an ingenious solution: to seal all liquids in an airtight bag with a single valve, so that astronauts can still have their coffee first thing in the morning. Let's take another look at Pedro Duque making his coffee. Here we can see one of the most important things about matter: its state. There are three states of matter: liquid, solid, gaseous. The liquid coffee, the solid bag containing it, and the air that surrounds them, which is a mixture of gases. Take a look around your everyday environment and you will see examples of the three states everywhere: air that we breathe, liquids that we drink or swim in or bathe ourselves with, solids that we build with or cycle to school on or play sport with. Understanding how these states can be changed has radically affected our technological development. These students are going to attempt to form all three states. Under normal atmospheric pressure, substances change state according to their temperature. So ice, when heated, becomes liquid water, and water, when heated, becomes a gas. Well done, boys! When water is heated to 100 degrees Celsius, it begins to change state, and bubbles of water vapour form inside the liquid. These bubbles rise to the surface and release vapour into the atmosphere. This process is what we call boiling. It is continuous and lasts until the water has completely evaporated. In weightlessness, the same boiling process occurs, but the bubbles do not rise to the surface. They stay where they are formed and merge together to create giant bubbles in the middle of the liquid. Not all substances change state at the same temperature. For example, oil becomes a gas at a much higher temperature than water. Take a look at the chip experiment. Water becomes a gas at 100 degrees Celsius. Not bad. However, oil doesn't change state until it reaches 300 degrees Celsius. So it gets much hotter, and those chips get crispier. You may wonder what's going on here, but these students are actually demonstrating an important thing about matter, which is that it behaves in different ways when it's in different states. When matter forms in a solid state, the molecules aren't free to move around. They can only vibrate. Increase the temperature and the matter changes to a liquid state. The molecules are loosely bonded together and flow, like this group. Increase the temperature again and it becomes a gas. The individual energetic molecules can diffuse wherever they want to. Gas molecules can move and disperse outwards, which is why smells travel. That's why you can smell the coffee before you see the cafe. We saw Pedro making coffee. Do you think the solid coffee became a liquid? Was it because the water was hot? But coffee also dissolves in cold water. The coffee is not changing state. The coffee is soluble and dissolves in the water. Not all solids are soluble. Try dissolving a plastic football in the rain, for example. A liquid which dissolves solids is called a solvent. White spirits or nail varnish remover are some everyday examples, and so is water. A solid which dissolves in a solvent is called a solute. Examples are sugar, coffee granules, and salt. When a solute is dissolved in a solvent, we get what is called a solution. The solid particles separate from each other and mix with the liquid. Usually the solid structure breaks up into its building blocks. These can be molecules or ions. Some substances are less soluble than others. Here we can see that as more and more salt is added to the water, only some of it will dissolve. This means the solution has become saturated. Here, sugar is being dissolved in hot water until the solution is saturated. Once it cools down, you can see the crystals forming. Sometimes when you mix a liquid like water with a solid, like this vitamin tablet, it doesn't simply dissolve. You get a chemical reaction and new compounds are formed. Heat is generated by the reaction, and carbon dioxide gas, a new compound, is released as a byproduct. This is why the tablet fizzes. Unlike a state change where ice, when melted, becomes water, chemical reactions are more difficult to reverse. You can't easily turn this tablet back into its original state. What are the film canisters for? We have a fizzy tablet in an enclosed space. It's going to be an explosive result. Wow! The tablet reacted with the water, releasing a gas. A gas always travels from an area of high pressure, such as here, inside the container, to an area of lower pressure, outside the container. The released gas creates thrust, which causes the container to go shooting up into the air, leaving the lid behind. Rocket engines use a similar principle. Our entire weather system is based on matter changing state. Water evaporates into the atmosphere. This water vapour then cools down again and becomes liquid, where it falls as rain, or freezes and falls as snow. Our oceans, rivers and climates depend on this process. On board the ISS, water vapour is reclaimed from the cabin atmosphere and fed back into the water tanks for recycling and consumption by the astronauts. Microwaves, fridges, cars, airplanes and even rockets are among the things we take for granted, but all depend on our ability to change matter from one state to another. But now let's look at ways to identify different types of matter by investigating their properties. Matter doesn't just vary according to atomic or molecular structure. Small differences at atomic level make a big difference in the everyday world. These differences can be observed and measured, giving different kinds of matter different properties. One of these properties is density. Density is a measure of mass per unit of volume. The higher an object's density, the higher its mass per unit volume. To put it another way, this volume of mercury will have the same mass as this much greater volume of water. A solid metal ball has a greater mass than a ping pong ball or a solid wooden ball of the same size because metals are denser. Refreshments. Squash and water have different densities. The squash remains near the bottom of the glass as it is denser. The water layer remains on top. But it's easy to mix the water and squash together again. Miscibility, or the ability to mix, is another property of matter. We say that two substances are mixed if they can diffuse into each other and if they are present in the same ratio throughout the mixture. Different substances mix in different ways, mainly because of the shape of the molecules. Wine and vinegar have similarly shaped molecules, which can easily create electrical bonds, and so they mix well. Oil and water, on the other hand, have different shaped molecules. This means that oil molecules prefer to stick to each other than to water molecules, and vice versa. Oil is also less dense than water and floats on top of it. Oil and water can mix to some extent, but on Earth they will always separate again because of gravity. Air and water also do not mix. What happens in weightlessness? On board this parabolic flight, we are watching a bottle containing air and purple-dyed water. When the weightless phase of the flight begins, you can see that they stay separated, but the air tends to form a bubble trapped inside the water. Here on board the ISS, we see the same thing. Different elements and compounds can also be distinguished by colour, and often we call colours after particular elements. For example, gold, silver and copper are the names of colours derived from these three elements. Another property of matter is surface tension. This causes the surface of a liquid to act as a thin elastic film, which is why you can sometimes overfill a glass without the water spilling out. Here, the force of attraction between the molecules allows them to cling together rather than flow out of the glass. Surface tension explains why water forms droplets. It applies to all liquids, and in space, where it doesn't have to contend with gravity, we can see it more clearly. Surface tension also explains why insects can walk on water. Let's see why. This sheet of aluminium foil is denser than water, but when it's spread out over a large enough area, surface tension will hold it up. When we fold this same sheet so that it covers half as much area, surface tension still supports the weight of the metal foil. If we fold it again and again, the area that the foil covers finally becomes too small, and the surface tension of the water can't support the weight of the aluminium foil anymore. Look at this. It's just water dyed purple, but you can see how surface tension helps the water form a thin film. This is because in weightlessness, without gravity to pull them apart, the attraction between the water molecules holds them in place. On Earth, this experiment is a total failure. You can't blow bubbles with plain water. It just won't form a film unless we use soap. You can create hundreds of bubbles by mixing vinegar and sodium bicarbonate. But it doesn't last long. Once the bubbles are created, they collapse back into a liquid state. That's because gravity pulls the bubbles apart, dragging the molecules away from each other and back down to Earth. We have seen that matter is formed and behaves in many weird and wonderful ways. Matter is made up of tiny subatomic particles. These then form atoms, which make up more than 100 elements. These elements can form molecules and compounds. Electrical charges play a big part in how matter arranges itself. Matter takes on three different states: solid, liquid, and gaseous. The close-packed atoms in solids vibrate. In liquids, the atoms can move more freely. And in gases, the atoms can diffuse. As we've seen, we can characterize different types of matter by their properties, such as density, miscibility, color, and surface tension. Matter exists from here to the farthest reaches of the universe. It is the bond between us and everything in the world around us, linking us to our most distant neighbours, the stars.